All right. Thank you very much, Arun, for the introduction. I have to say that the title of the presentation is a bit far from what we understand from foundations of communication networks, but you will see that the decision to include this talk in this series is because the mathematical objects that we will be dealing with are born or issued from our community. So I'm happy to present this work here. Let me start first by acknowledging the contributions of two PhD students, Xingyin Zhu at INRIA and Francisco Daunas at Sheffield, and two faculty as well, Iñaki Naolan and Vince Poor. Right. So what I would like to propose for the talk is to first formalize the idea of generalization error, and then present two optimization problems that are at the first sight very uncorrelated from the idea of generalization error. We will try to make this connection between these two objects through something that we will call the method of gaps. And then for ending the presentation, what I suggest is to walk through a number of explicit expressions for the generalization error that we can obtain from this method. All right? Okay, so with no further introduction, let's admit the existence of an information source that provides us with pairs of patterns and labels. So these patterns can be, for instance, images of cupcakes and chihuahuas. And the label is exactly what we have inside the photo, right? So we can admit that this pair, this tuple of pairs of 16 in this case, is going to be used as a training data set for what we will call an algorithm. A machine learning algorithm. And a machine learning algorithm in this talk is going to be understood as a probability distribution over the models that we will call theta, conditioned on a data set, right? So for each data set, we will have a probability distribution over the models. And this is an idea that I would like you to keep in mind, because this is what we will call as an algorithm. Right. So what can we do with that probability measure, or with that algorithm? Well, we can sample the probability measure and obtain a theta that can be interpreted, for instance, as the weights of a neural network that we can call, for instance, age. And what we will do is that new photos will be put at the input of that neural network, and we expect to have the right label. Right. So how to test that algorithm? Well, we can ask for another data set that we are going to use for testing, and each of these pairs are going to be put at the neural network. So the image takes the input of the neural network, and when we compare the output of the neural network with the label that we were supposed to observe. So that comparison is done by this function L that we will call the loss function or risk function. So if the two labels are the same, with this function is going to be 0. Otherwise, depending on the distance of these two labels, we will have a positive real number. Right. So we have n pairs here of photos and labels. So for each one, we can calculate the loss, and we can calculate indeed the average loss, which we are going to refer to as the empirical risk. In this case, the empirical risk is calculated over the test data set U. So it appears here as one of the arguments of the function L that is giving us the empirical risk, and theta, which is the model that we are going to use as the weights of this neural network. Right, so we can do the same with the training data set, and we will obtain then the training empirical risk, right? So here the argument is Z, because our training data set has been called Z, right? and let us not forget that the idea here is to sample the probability distribution that we recognize as an algorithm, right? And use that sample model each time that new data is coming. So it makes a lot of sense to think of the expectation of the expected of the empirical risk when the data set is kept fixed. So in this case, we keep fixed the test data set, and in this case, we keep fixed the training data set, and we make the models vary according to our algorithm. So essentially, what we have here is an expectation, right? So If
Can I interrupt? I have just one question.
Sure.
Yeah. So if you go, okay, let me understand this correctly. So your first Z is your basic training set, and it puts
Yes.
on your model class, right? Theta is your weights, and it puts a distribution on your theta. So you sample theta. Now, what is so this is a validation test data set, is it? The validation, is that the second branch, is that the validation data set kind of a thing?
Yeah, we can call it like that. Yeah. It's something we are going to use to indeed validate the algorithm. So yes, exactly.
But what is this H? So this H is what?
What is this age? Age can be, for instance, so if theta, if theta are the weights of a neural network, age would be the neural network, right? So the neural network takes the weights, right, vectorized as in the form of theta, right, and then it receives an image, uh, um, right, and then provide us with the label.
Okay, okay. And what is X is now a sample of the data. X is a sample of the data which you want to label. And what is so L is your loss function, is it? So mu is mu your correct label, the new correct label, the new.
Well, we assume that exactly, very good point. So we are assuming that this photo here, mu I, right, is associated with this label, and we obtain this from the source. So
Ah,
we compare the output of the neural network with that label that has been given to us.
actual label. That's the true label. So this is the
Exactly.
between so you've been trained to theta and you've given the sample X, you get an outcome H, and then the true label is U. This is the loss function. Correct?
There you go. Exactly.
Go ahead, please.
Okay, right. So we were saying that we can calculate empirical risks for both data sets, right? And we can take expectations because indeed this data is sampled from the probability distribution that describes our algorithm, right? And we will end up with these objects that I denote by RZ. So this is the expected empirical risk when the data set has been kept fixed at Z, right? And models are being chosen randomly from this probability distribution, right? So I was about to say that if the difference of these two values does not vary too much or is sufficiently close, they are sufficiently close to each other, we can say that the algorithm is generalizing well over that test data set, right? And for the practitioner, essentially the story ends here because training data set and test data set is the only data available for the in practice, right? If we want to further the analysis of this, we need to admit some assumptions. We may admit, for instance, that training and test data sets are identically distributed and are independent. For instance, here I'm choosing as the distribution of the data set this PZ with Z in boldface, right? So if we admit that, we can, for instance, take the expectation of that difference of errors, and this is exactly what we understand as generalization error. All right. So this may be yes.
So your expectation is going to be, you will not, I mean, so you're going to do uniform convergence, right? So your expectation is going to be over all distributions or because you don't know P, correct? I mean, you don't know the distribution of the underlying data, correct?
Exactly. So for defining the generalization error, we need to make an assumption, and we say, well, data comes from this PZ. Indeed, that is an unknown distribution.
Okay.
Yes, yes, indeed. Exactly. All right. So let me read equation two for you. So the left-hand side is this G double bar. There are two bars because there are essentially two integrals. That's not very important. What is important is that the algorithm that we are studying is characterized by this conditional probability distribution P theta given Z, right? And the data is assumed to be drawn from this distribution PZ that, as Arun mentioned, is not known. Right. So what do we have on the right? On the right, we have an expectation, so a double expectation indeed with respect to these two probability measures. But the key word here is that we are taking the expectation of the variation of the functional R, right? When the data set varies from the training data set to the test data set, right? So seeing the generalization error as a variation of a given functional, I say functional because it receives as an argument a function. So this is a function of a function. Is the key of this presentation. Okay, so the generalization error is seen as the variation of this functional when the data set changes from the training to the test. All right. So what I propose now is to study two optimization problems that are apparently very uncorrelated with the idea of generalization, and then try to connect this with the, with the calculation of generalization error. All right. So let's do this. Problem one.
Sorry, once again.
Yes.
Go back. Because I think that equation is very important. So I would want to kind of, just elaborate a little bit more here. So the last equation. So the left, both the, I mean, so the Z is isn't the PZs the same? Like of the Z
Yes.
and the Z on the right, isn't the PZs the same?
Exactly. So we have an assumption. We say both training and test are sampled from the same probability distribution, but they are independent. So that's why we see here the product of two, two measures, but these two measures are the same measure in the PZ, is the measure of the data.
Okay, thank you.
Yes. That is key. That is very important. And I want to say as well that probably this is not the phase, meaning the expression that you find in books of the generalization error. But I promise you that if you work out a little bit algebraically this expression, you can find all the expressions that you find in the books. I am using this one in particular because this expression is the one that has opened our minds for actually developing this theory. All right, so let me formalize two optimization problems. All right, so for the first one, we are going to fix the data set Z, all right, here, and a reference measure Q on the models. Okay, this can be seen, for instance, as a prior. And we will have a positive real lambda. What is the problem? The problem is the minimization of the expectation of the empirical risk for that fixed data set when models are chosen from the distribution P, right? And a regularization, which is positive lambda times Kullback-Leibler divergence of P with respect to Q, all right? I will call Kullback-Leibler relative entropy is the same. Okay, and this is the formalization of the first problem. The optimization domain, of course, are all the probability measures on the models that are absolutely continuous with the reference measure. That's important. All right. This problem has been deeply studied in this reference I am providing here under. Problem 2. In this case, we require fixing a model theta, right? And a reference measure PS on the data points and a positive real beta. In this case, we are maximizing the loss for a fixed model when data points XY are sampled from the probability distribution P. The regularization in this case is negative beta relative entropy of P with respect to PS. And the optimization domain is formed by all probability measures on the pairs X and Y that are absolutely continuous with PS. All right, so two apparently very simple problems. This second problem has been studied in this paper I am mentioning here. And we will see that it is associated with a sort of a worst case data generating probability measure. Right. Problem 1. Let's go into the details now of this first problem. The problem that we want to solve is the one in 5, right? And just for not, yes.
Can you give more intuition on the two problems? Because I think that's important to understand. So what does the first one do and what does the second one do?
Right, so that's a very good point. Let's see intuitions here. So let's focus on lambda for a moment. And we can see that, for instance, if lambda is 0, right? The optimization problem is essentially the minimization of the empirical risk. So P is going to be a measure concentrated on the minima of the empirical risk. If lambda, on the contrary, is very big, right, we are going to have a solution that is very close to Q, right? So what we are doing here is trading how much we trust the data set, right, so that we can generate a probability measure P that minimizes that loss, right, or how much we trust our prior Q. Lambda is the parameter that is going to allow us to trace between optimization of the empirical risk or similarity with the prior Q. And we observe something very similar here in equation 4, right? This is a maximization. So when beta is very big, we are giving a lot of importance to the similarity to the reference measure PS, or the maximization, right? In the other case, the maximization of the expected loss for a fixed theta, right? So remember that in this problem, theta is fixed. So that is more or less the intuition. I can go on these intuitions, Arun. What do you think? Is it clear?
Yeah. Sorry. Yes. Go ahead, please.
All right. So let's focus on problem 1. What I have here in equation 6 is a function, right, parameterized by the reference Q and the dataset Z, and it is essentially the logarithm of the moment generating function of the empirical risk for a fixed Z, which is a parameter of the problem, when the models theta are chosen from the probability distribution Q. Okay, I am pointing out this function because we use it for the description of the solution of the problem. You are not going to see this function again in the talk, but I want to highlight that this function exhibits a number of properties that are extremely important in the proofs of everything that I am going to show. Just for the experts, keep that in mind. This is a very important function. Right, the solution of the problem in 5 is unique, and we have denoted it with the parameters Q and lambda in parentheses, and the Radon-Nikodym derivative of the solution with respect to the reference measure Q is equal to this expression that we have on the right. In case you don't remember what the Radon-Nikodym derivative is, let me tell you. If Q is chosen to be the Lebesgue measure, all this left-hand side is simply the probability density function of the solution. If Q, the reference measure, is the counting measure, for instance, then this is going to be the left-hand side is going to be the probability mass function. If Q is chosen as a probability measure with either a PMF or a PDF, this left-hand side can be just as can be seen just as the fraction of the density of the solution with the density of Q, right? Okay, I promise that you guys have seen this before if I write it like this, for instance. So here the solution essentially is assigning probability exponentially inversely to the value of the empirical risk. For instance, models that induce a high empirical risk with respect to this data set are going to receive very low probability, right? And the denominator is simply there for ensuring that this is actually a probability measure. So you see that the denominator is exactly what we have here in equation 10, right? So key point, this is a Gibbs probability measure. The solution to this problem is a Gibbs probability measure. Right, so let's start now connecting this to the variations of the functional RZ, which is the main target of our talk. So what we see, yes, Arun.
Previous slide. So KQZ, if I understand correctly, is the moment generating function of the loss with respect to your prior distribution on Q. So you want to really, in some sense, minimize this over Q so that you decide a good prior. I mean, not really minimize. Well, this contains all moments, so I don't know what to do. But is that the intuition? Is that correct?
No. Well, I mean, we can develop that idea indeed. My suggestion for this talk is just to see that function KQZ is essentially what we need to normalize this for being a probability measure.
Okay.
If we keep it as simple as that, I think it's better because I mean, you're right. I mean, there are a lot of properties, but let us keep it simple. Let us keep this KQZ as what we need in this function for this to integrate to one. Okay. Okay, so let's go on with that. Now, what I want to show you is an amazing property of this problem and its solution, and is the following. RZP, which is what you see here, this is the expectation of the empirical risk for fixed Z when models are chosen from P, right? That is the definition of the functional. We see that when we deviate from the optimal, meaning the solution to the problem, to an arbitrary probability measure, the variation of this functional RZ is equal to lambda times three terms that are given in relative entropies. And what is interesting there is that if we associate relative entropies to pseudo distances or statistical distances between measures, we are actually there comparing the optimal with the reference measure, the deviation P with the optimal measure, and the deviation with the reference measure. There is indeed a geometric interpretation of this. I'm not going to spend time because I'm being a little bit delayed now. But if you have questions, we can come back to that. The key point is that in the same way we can characterize deviations from the optimal to an arbitrary probability measure, we can also characterize deviations from an arbitrary probability measure to another arbitrary probability measure. This result is then extremely powerful, is new, and I think that if you have ever used the Baradan formulation of KL divergence to calculate difference of expectations, you may be very interested in knowing how this expression is obtained, because it's actually is not giving us an upper bound, but instead the value with the quality of that variation. Right. We can tell a lot about this expression with now 4 relative entropies, but I propose that we advance and then rather focus on the algebraic transformations that we can do of this expression. All right, we will come back to it in a while. Right. Problem 2. Problem 2 has a similar structure, so we can also define a cumulant generating function G that is not going to appear in the talk, but has a lot of properties and plays an important role in the proofs, and admit that the solution is also a Gibbs measure. This time, the highest probability is given to models, to data points X and Y that generate a high loss. Okay, and this function GPS theta is there just for making this to integrate to 1, for making the solution to be actually a probability measure. Okay, so when I say that high probability is given to pairs that actually maximize L, right, we find quickly a justification of why we call this solution to the problem the worst case data generating probability measure. Okay, it's because for this particular model theta, for that particular L function, this probability distribution is generating data points that generate high losses with high probability. All right, so this is the idea behind this. And again, if we deviate from the optimal to an arbitrary distribution, we can write that deviation or that variation in terms of 3 terms, including the worst case data generating probability measure, the reference measure PS, and P, which is the probability measure to which we are deviating. Bigger than this result is that we can also formalize deviations from an arbitrary P2 to another arbitrary P1. And this is given in terms of, again, 4 relative entropies involving the worst case data generating probability measure. Okay, so now you start thinking, oh, I see probably the connection between generalization error and these 2 optimization problems, because what we have done so far is obtaining closed form expression in terms of information measures, here relative entropies, right, of the variations of the empirical risk. When we keep fixed the data set and we vary the algorithm, I say algorithm because these probability measures P1 and P2 can be assimilated as algorithms following our definition, or the variation of the expectation of the empirical risk when the model is kept fixed and the data varies from P2 to P1. Okay? So I will call these expressions the normal expressions for these variations in the rest of the talk. And these are the most general expressions in terms of information measures because we require very mild conditions of absolute continuity and so on. All right. So with these elements, we are ready to introduce the method of gaps. I would make a break here to ask whether you guys have any question concerning the last part.
Just some intuition on the previous two theorems. I mean, if you can provide some broad level English, that'll help. Thank you.
Thank you, Arun. The rest of the talk consists exactly on providing you intuitions of these two theorems. What I'm going to do from now on is to walk you through many expressions that are equivalent to what we see on the screen now, and what we are going to do is to try to use those equivalent expressions for getting some intuitions. Right, you're right. Actually, I mean, we can stop the talk now and say, okay, this is we were invited to provide expressions for the generalization error in terms of information measures. We did the job at slide number 16, right? But as you mentioned, giving an insight of these expressions is very difficult. So what I would suggest is to introduce the method of gaps formally, right, so that we can obtain actually expressions for the generalization error, and then provide some intuitions. Yes?
One quick question. M is your space of all neural network weights, is it? Model class. I mean, I don't know whether I should use the word model class. Is that correct?
I'm having trouble to listen. Aaron, can you please repeat?
Script M in your previous slide is the space of all neural network weights. Is that correct?
M, you mean M, this one?
Yeah.
Yeah, exactly. So this is the set of models indeed. Yes. The set of all possible, exactly, very good. The set of all possible weights that we can use for that network. I use the neural network as an example because the function age can be any learning object, right?
Yeah.
That can be parameterized by a vector theta.
What is interesting is your statements don't depend on the size of M, which is
Very
okay.
good point, Aaron. Excellent point, actually. Yeah. So the n, the number of points that I have in the training is here, because this depends on Z, which is the training data set. So my training data set, right, is determining this Gibbs probability distribution.
Okay. Go ahead. Thank you.
Yeah. On the other side, there is no n in the second expression because we have assumed that this is IID, right? So the sums, when we divide 1 over n, the sums, that idea of n, given that everything is IID, disappears. But the key point is that we can obtain the same expression from either theorem here. Right. Let me then introduce the method of gaps formally. This is just notation for you to have it in mind, right? What is important here are two essential observations. The first one is that the generalization error is an expectation of the variation of these functionals Rz or R theta. This is the main observation that will allow us to build the theory. Now, these variations that we will call gaps from now on, they exhibit interesting properties and closed form expressions that we have seen in terms of information measures. So the method of gaps can be described quickly as a two-step method in which the first step is to express the generalization error as an expectation of a gap. This is what we are going to do right now. And the second step is, well, use the properties of gaps for obtaining the closed form expression that you like the most or that you need the most, right? So to continue, there are two types of gaps. One in which we keep fix the training data set and we vary the models. This is called an algorithm-driven gap, because, as I said, P1 and P2 can be seen essentially as algorithms. Now, when we keep fixed theta and we vary the distribution of the data, we are going to call these gaps data-driven gaps, because those are variations due to the change of the data. The first one is a variation due to the change on the algorithm. All right, so this brings us to two variants of the method. The first one in which we are going to use the algorithm-driven gaps, and in that case, we will be dealing with the Gibbs algorithm. And essentially, this method is going to tell us, well, if you want to calculate the generalization error of a given algorithm, what you have to do is to compare it with the Gibbs algorithm. And this is one of the big conclusions of this work. That variant, based on algorithm-driven gaps, is very general in the sense that there are no assumptions on the data probability distribution (PZ). Right. The second method, data-driven gaps, are going to be in terms of the worst-case data-generating probability measure. Right, and we are going to be there rather focusing on the variation of the data, right, instead of the variation of the algorithm. Right. This method, this variant of the method requires the IID assumption, meaning that the data points are IID. And we will denote the probability distribution of the data points, meaning the components of the data set, at PZ. There is no bold font here, and there is bold font here. So this is the tuple of n data points, and this is only one data point. Right. With this in mind, let's write again our formula for the generalization error. We see there that this is a variation when the data set, right, changes from Z to U. And this is the only variation that we haven't characterized. We characterized when the measure changes, when the other things change, but this is something we haven't done yet. So our objective now is to write the generalization error in terms of what we have done before. Let's do that. Step one, I can write the generalization error of the algorithm P theta Z when the data sets follow the distribution PZ. So this is a distribution over the data sets. So there may be correlations inside the data points. And this is equal to expectation of this gap, right? And this is a gap that appears when the data set is kept fixed and the algorithm changes from this instance. I mean, this is the algorithm trained over Z, the same set here, right? And it changes to a sort of a barycenter. So from the probability point of view, this is just the marginal of the product P theta given Z times PZ, right? So this is the marginal of the joint. But intuition-wise, we are changing an algorithm that depends on the training, right? The algorithm we are studying, to an algorithm that does not depend on the training data set. And if you see the expression of P theta, this is a sort of a barycenter of all possible instances of the algorithm that we can build. Everybody sees this, right? Because we get this instance here, which is a probability measure. We multiply it by the probability of that data set, and we continue the sum, right, through this integral. Okay, so that is the first intuition of that expression in 28. Now, if we use the previous results that we have obtained, we have an explicit expression for this variation in terms of information measures with the four relative entropies. So now, if we plug in that result, we obtain a clean expression of the generalization error in terms of these four terms. And still, this expression is difficult. You can tell me it's difficult to obtain an intuition. And I admit that it is difficult to obtain an intuition. It is difficult to calculate, and it is very difficult in general. So why are we interested in writing something that was understandable by everyone, right? Just difference of expectations in terms of something that are relative entropies and so on and so on. Well, there are many reasons for doing that. The first one is that through this transformation of the problem from a vector space, right? In the models are in a vector space for dimension D, right? RD. Here we are passing through the analysis of probability measures. And there is a particular probability measure that comes up that corresponds to a well-known algorithm, which is the Gibbs algorithm. All right. So by complicating a little bit the statement or the expression of the generalization error, we have the opportunity now to bring an object that is very well known, that has a lot of properties that have been studied by many communities, statistical physics, information theory, game theory, etc., to the analysis of this problem. Okay, so there are reasons for admitting this expression. Now, if we go to the other variant, the data-driven gap, right? We are going to obtain that the generalization error is also an expectation of another gap. In this case, right? There is a variation for a fixed model theta from a measure that is very particular. Why I'm saying it is particular? Because we said a machine learning algorithm is a measure p theta given z. And that algorithm can be considered as the posterior on the models given the observation of the data. This explains actually the optimization problem that we solve. So what we see here actually is the likelihood. So if we take values and we transform that posterior into a likelihood, this is what we hear. This is what we see here. And what we are observing is that the generalization error is the expectation of the gap when the data changes from the likelihood for that particular theta to the actual distribution of the data points. All right. And with the expressions that we have obtained before through the optimization problem, so on and so on, we can indeed build an expression in terms of these four relative entropies in terms of the worst case data generating probability measure. All right. So now we can say that so far we have finally explicit expressions in terms of information measures, right? Of our generalization error, right? So what I would suggest now is to work out this expression so that we can provide some insights and meanings and connections to other areas. Any question concerning this the third part? Okay, if there are no questions, let me start saying that particular choices of the parameters Q, PS, lambda, and beta will lead already to expressions that are very familiar to us. The problem is that algebraic manipulations of these two closed forms that I just show will, of course, lead to less generality. The more we manipulate these expressions, the less general they become, because every manipulation requires new conditions, either on the algorithm or the data generating distribution. Okay? The interesting part is that these expressions will allow us to create bridges to areas that are very familiar to us. Let me build one very interesting one with the notion of hypothesis testing. So this is an expression that has been worked out. There are no more relative entropies, but what we see here in red is the radon-Nikodym derivative of the solution to the problem 1 that we saw at the beginning. And we see here a difference of the logarithm of that radon-Nikodym derivative, right? And expectations with two probability distributions that are actually very familiar to us. This is the product of the marginals, whereas this is the joint probability distribution. Okay, let's try to understand a little bit more this expression. Let's first realize that if we assume that data sets are chosen from PZ and models are chosen from the Gibbs algorithm, right? The random derivative of this joint distribution with respect to the product of the reference and PZ is exactly what we have inside the logarithm in the first expression. Okay, so what is this? What is this expression in black and what is this expression in red in equation 34? Well, key point, models are being generated from the algorithm and data is being generated from the ground truth distribution. So the ground truth probability distribution of these random variables theta and z is this distribution. We can create a hypothesis test to ask whether an observation of a pair theta z comes from the product of Gibbs algorithm times pz, so the ground truth of the data, or models and data sets are independent following Q times PZ. In that case, we are going to build the log likelihood ratio of that hypothesis test problem, and we will end up realizing that that log likelihood ratio is exactly what we have in red in the first expression. So what are we left to? First of all, we need to recognize that this is a kind of weird hypothesis test because neither the null hypothesis nor the alternative hypothesis is the ground truth probability distribution. So this is a class of hypothesis tests that are called mismatch hypothesis tests and were introduced very recently by the team of Albert Guillén y Fabregas in Cambridge University. Right. So if we continue with that, we can read that expression as follows. We can understand the generalization error as the variation of the expected log likelihood of that hypothesis test when the ground truth changes from an independent distribution to the joint distribution. Okay, and once we have admitted that, then all the results that exist from mismatch hypothesis testing are applicable to the analysis of generalization error. Okay, so this is my first intuition on the expression. Arun, yes.
So you are looking at, so if I understand the previous expression correctly, you're doing the expectation of a functional with respect to two measures. One is the product, one is the joint measure, and the other one is the product measure. And
Exactly.
you are trying to take the expectation of is the random equivalent derivative of the log of the random equivalent derivative of between two distributions, the log of that, right?
Exactly.
What I mean, I haven't thought about this object. What is it that this will I mean, what is it that this will kind of quantify or, I doubt any of us would have thought about this.
Arun, can you repeat the last part of the question, please?
So what does it quantify? So you're looking, see, I
Oh,
understand.
okay. Yeah, got it. Got it. So what is this? What is this number that is in red there? So we say if that number is bigger than a given gamma that we fixed, then we choose hypothesis, null hypothesis. If this is smaller than that value, we will choose the alternative hypothesis. And what is this value gamma that with which we compare this red value? Well, you know that there are type 1 and type 2 probability of errors in these hypothesis tests, right? So this number in red is the one that allow me to get given the observation theta and z, right? I get this number, I compare it with my lambda, and then I take the decision on which hypothesis I take. This is, sorry, I was not clear enough. This is exactly the log likelihood threshold if we want to associate it with hypothesis tests.
Okay, thank you.
Exactly. So yeah, exactly. So that is the key point, actually. Thank you, Arun. The key point of this slide is that an object that appeared, right, in the first problem that we can use to write the generalization error has a very interesting functional meaning in a statistical hypothesis test, in particular in this new class of hypothesis tests introduced by Albert in 2022. Okay, so that's why I'm saying all these results that we have from this new class of hypothesis tests is something that we may end up using here for the analysis of generalization. Thank you very much, Arun. Right. So if we now use not the algorithm-driven gap, but data-driven gap, we obtain again an expression that is very similar to the one that we have already analyzed and has exactly the same interpretation in the context of hypothesis testing, mismatch hypothesis testing, indeed. Okay, let me now establish connections with information measures, okay? And let's do very simple stuff. Let's choose the reference measure Q, right, as, for instance, the marginal p theta. If we do that, we obtain immediately a mutual information term. So we say generalization error is equal to a mutual information between data and models, plus a term, a beautiful term, because it is essentially the comparison to relative entropy of the algorithm that we are studying with the Gibbs algorithm. Okay, the other term has the same flavor. Remember that this p theta can be seen as the barycenter of your algorithm, right? Because this is the marginal of this posterior when the data is pz. Okay, so on the right hand side we get the mutual information plus a term that is essentially comparing your algorithm with the Gibbs algorithm. If we do that the same in the data-driven case, we obtain negative mutual information plus a term that is essentially comparing the data distribution with the worst case data distribution. All right. So if you are interested in data poisoning of machine learning algorithms, the expression that I have here in the second square is a key expression because it is telling you how your generalization error changes when the data changes in terms of closeness to the worst case data generating probability measure. Key point, what I am providing here are exact expressions. These are not upper bounds, not lower bounds. These are exact expressions. If you want to build upper lower bounds, well, you can exploit the fact that these relative entropies, when the reference measures are probability measures, are always positive. Okay, good. So I am really behind the time. We can continue making choices of Q, the reference measure in the first variant and in the second variant, and we will continue getting expressions, beautiful expressions. In this one, for instance, what we see is the Lawton information, negative Lawton, and here it appears positive Lawton. And Arun was asking where n, the number of data points, is, and here you have again that that n that appears explicitly. All right. If you don't see it in the first expression, it's because indeed n is the length of this vector z, which is our training training data sets. Okay, I want to make an emphasis on two particular expressions. One in which we actually find the mutual information and the Lawton information, plus the sum of these two terms. Okay, and why I want to do that is because I want to ask this question: why, if the term in the second line of the equation is zero? So we will obtain a very beautiful expression that says generalization error is exactly lambda times mutual information plus Lawton information. And it's very easy to see that if the algorithm that we are studying is the Gibbs algorithm, right? So this Radon-Nikodym derivative will become 1, logarithm of 1, 0, 0 on the other side, so this becomes 0. And then we conclude a result that has been already found by Golamali Aminian and his team, right? That he says the generalization error of the Gibbs algorithm is exactly the mutual information plus Lawton information. The case of this expression from the variant of data-driven gaps is equally interesting because we can ask the same question. What if that second line is equal to 0? There exists an algorithm for which this expression is 0. And then in that case, the generalization error of that algorithm would be negative beta divided by n times mutual information plus Lawton information. Well, it turns out that that algorithm exists and is the one that generates as likelihood on the data given the model, the worst case data generating probability distribution. Okay? My student Xingying Zhu is actively working on the analysis of that algorithm, and so far she has found a lot of interesting properties of that algorithm, and probably, hopefully, she will be giving a talk about that algorithm alone soon. I want to come back to this. This is the existence of that algorithm is actually a very important step in this analysis, because essentially this is an algorithm that generates negative generalization error, right? And remember that there is this trade-off between generalization error, so how good you do when you know the distribution of the data, and how good you do when you are essentially working only with the data sets. Okay, so I want to close this walk through the garden of equivalent expressions for the generalization error with this one in particular, because it has only two relative entropies. One that is the comparison of the algorithm that we are studying to the Gibbs, when the Gibbs and the algorithm under study have been trained on different data sets, and those data sets are chosen identically distributed but independent. And another term that characterizes the relative entropy between the algorithm trained with the same data set as the one used to train the Gibbs algorithm. Okay, so this expression to end, I would like to end with this expression, because this expression probably is the one that is the most the simplest, and shows us that essentially calculating the generalization error of a given algorithm, any algorithm, consists essentially in comparing it with the Gibbs algorithm. All right, and then the expression on the right allows us to change Q and lambda as we wish. I mean, of course, satisfying the constraints that we have in the theorem. But we have seen that the choice of Q and lambda actually may ease either the understanding of these expressions or actually the calculations, because the choice of Q as, for instance, Lebesgue measure or Contin measures make this measure here, the Gibbs measure, to be extremely simple. All right, so there is indeed a geometric interpretation of this. I prefer to go to the concluding remarks to finally show a small example of how this works, and to start wrapping up. Questions before we go to this next part?
Hey, one question about that figure. So if I understand correctly, the divergence doesn't satisfy the Pythagoras theorem, right? So it's the parallelogram law, or what is going on here?
Well, you got it completely, actually, because so here we have an average. First of all, we have an average of this pseudo distance, right, between p theta given z for that particular z with the Gibbs algorithm. And what we have on the sides are distances, pseudo distances indeed, of actually this is let me, I mean, we want to go into that analysis. Let me use the first one. That is way easier to use, because that the expectation here adds a lot of noise for the analysis. This one is easier. We have the relative entropy of P with respect to Q. Okay, we know that if we put another measure, for instance, the optimal measure here, the relative entropy from P to that optimal and the relative entropy from the optimal to Q is not equal to the pseudo distance from P to Q, right? This photo here is telling us what is the excess, right, that we need to add, so the error that we need to add for that to be an equality. And it turns out that what we have to add is exactly the variation of the functional RZ that we are studying. The variation from the optimal that appears here, and is the point that we have used as an intermediate point to calculate distance from P to Q. Am I being clear?
Yeah, I think I understand. See, the issue is that this 90 degrees is just, it is just, I mean, uh, that is just like a figurative, right? I mean, there's nothing true about it, if I understand correctly. What you're, when you write this diagram, what you're really saying is the square of the left plus the square of the, the square of the vertical and the square of the horizontal is equal to the square of the diagonal. But that's it, and nothing more. I mean, don't interpret it as orthogonal or anything. That's my understanding.
Well, okay, so you are right. You're right. I mean, we can stop there, and this is just the reverse Pythagoras theorem. But I have built a triangle here, right? When we analyze the other, I have built another triangle, and then you will see that there is this last triangle, right? And some sides of that triangles are the same, okay? So when I put all these triangles together, they lead to a figure that is the putting one triangle sharing one side, right? And that construction actually allowed me to use very simple arcosinus, arcotangent identities to calculate the terms that I don't know. So that's very powerful.
Okay.
Now, is this the evidence that there exists a geometry behind this? Well, there is the whole area of information geometry that tell us, yes, there is, right? The hypotenuse of this triangle is a geodesic actually between 2 points, and there is a proof for that.
Okay.
Yeah. So from my perspective, this is a very deep interpretation of all these values.
Thank you.
Okay. To conclude, we have studied the empirical risk optimization with relative entropy regularization. We studied the maximization that led to the worst case data generating probability measure and the minimization that led to the Gibbs algorithm. It turns out that the method of gaps allow us to provide expressions to the generalization error using either the Gibbs algorithm or the worst case data generating probability measure. Interestingly, the first method, algorithm-driven gaps, lead to comparing whatever algorithm to the Gibbs algorithm. The second case, data-driven gaps, is very appealing for studying data poisoning or secrecy or security of these systems when the metric, right, is the generalization error. Why? Is because that second variant focuses on variations of the data, okay, with respect to the worst case data generating probability measure. Right. So I want to end up with this paper of my colleague Panayotis Martikopoulos at CNRS. He asks this question. He says, what is the long-run distribution of the stochastic gradient descent? And he provides the answer to that question in his paper. He says, using an approach based on the theory of large deviation and randomly perturbated dynamical systems, we show that the long-run distribution of the stochastic gradient descent resembles the Gibbs distribution used in thermodynamics with temperature equal to the method's step size. So this is our lambda or beta, and energy levels determined by the problem's objective, meaning the loss function that we have defined. Right? Okay, so using that abstract, we can immediately create a corollary of that abstract and say, what is the long-run generalization error of a stochastic gradient descent? Well, we just have to plug in our expressions the long-run distribution of that algorithm, and what we obtain is sum of mutual information plus Lawton information times the step size of the algorithm that we are using. Okay, so with that example, I hope I convince you that this, despite the fact that these results are very theoretical, when the connection between algorithms and probability distribution is made, these tools that I have presented today give us immediate results. Right. So to finalize, please, if typos, comments, or questions arise, my email, samir.perlaza@inria.fr.